Here are solutions to homework set number 14 for ECE 111, Introduction to ECE. In this homework set, we're looking at using Matlab to analyze filters, to design and analyze them. So this kind of picks up where we left off last week. Last week, we looked at complex numbers and phasors. With phasors, I can represent sine waves. Well, if I have a filter is a circuit where the gain changes with frequency. It represents a differential equation. What I can do is I can find the output given the input using phasors. So this uses complex numbers quite a bit in Matlab. To illustrate that, let's look at problem number 1. The first problem is, suppose I have a transfer function. Here's a filter relating the input and the output. Now where this comes from, you'll get to that when you take Circuits 2, Electronics. This is a circuit with 3 capacitors in it. I know that because it's a third order differential equation. The number of poles tells the number of energy storage elements, like capacitors, inductors. But anyway, this is just a filter. What is the differential equation relating x and y? Well, to find that, I multiply out the polynomial. That's the command poly in Matlab. So here's the denominator polynomial multiplied out. Cross multiply. Then note, with Laplace, s means derivative. So this is the third derivative of y, second derivative, first derivative, y, first derivative of x. So this is the differential equation that corresponds to that transfer function. So anytime you see a different or transfer function in S, that means differential equation. Problem 2 is, suppose the input is a constant. And later on we'll look at a sine wave. When you take Calc 2, Calc 3, solving this problem is really, really hard. With phasors, it's actually really, really easy. If you don't mind complex numbers, this is actually a fairly easy problem. This is the gain. That's the gain everywhere. If I have a very specific input, like x equals 5, all I care about is what's the gain at a very specific frequency. In this case, at DC, s equals 0. That comes from everything's in the form of e to the st. If this is equal to 1, then s equals 0. The input is 5 times 1. So this is the gain everywhere. All I care about is what's the gain at DC times the input at DC, and I get a number. That represents the constant, 6.34. Now, in calculus, what you're going to do is guess the answer, take the derivative, substitute, solve. 30 minutes later, you get the answer. This is way, way, way faster. That's one of the reasons we like phasors. But you got to know complex numbers, be comfortable with complex numbers. One of the reasons I highly recommend getting a calculator that does complex numbers, because you're going to be doing complex numbers for the next 4 years. In Matlab, I can do that by saying s equals 0, x equals 5. This is the gain everywhere. All I care about is what's the gain at s equals 0 times the input. I get a constant. What is the output when the input's a sine wave? Now this is where phasors really shine. This is a really tough problem in calculus. Pretty easy using phasors. In this case, everything is in the form of e to the st. A sine wave means that it's in the form of e to the j3t. So s equals j3, that's this guy right here. X is 0 minus j5, real part's cosine minus j is sine. So the output is the gain at 3 radians per second times the input at 3 radians per second. Gives you, using Matlab, s is j3, there's x, multiply it all out, I get a complex number. Real part's cosine minus j is sine. Done. Now in tests, you may not have Matlab available. This is why you need a calculator that can do complex numbers. With an HB prime, what I do is I just do the numerator, 400, times s plus 1. S is equal to j3, so that's 1 plus j3. Multiply. This is 5 plus j3, divide, 7 plus j3, divide, 9 plus j3, divide, 0 minus j5, multiply, and there's your answer. What that means is the real part's cosine minus j is sine. This is a typical problem you'll see in Circuits 1, Circuits 2, Signals and Systems. This is kind of, again, why you need, highly recommend get a calculator that can do complex numbers. You're going to need it. You're going to use it. Problem 2. Slightly different problem. Suppose I don't know the specific frequency, but I know the range. Like, I want to know what's the gain of this guy for frequencies between 0 and 30 radians per second. Well, in Matlab, what I do is I just have frequency sweep between 0 and 30 radians per second, steps of 0.01. That's kind of arbitrary. That just means I've got 3,000 points I'm going to analyze. S is j omega. The gain, this guy right here, is the way you write it. 400 times s plus 1 divided by s plus 5 times s plus 7 times s plus 9. I need the dot notation. That tells Matlab, don't treat that like a matrix divide or matrix multiply. Treat that as 3,000 separate problems. Solve all 3,000 separately. When I'm done, I get a 3,000 by 1 vector. That's the gain at each frequency. It's a complex number, but the amplitude is the magnitude, the gain. So plotting the magnitude versus frequency, that's what I get. This tells you this is a bandpass filter. It passes frequencies near 5 radians per second, passes DC sort of well, and then blocks high frequencies. So as the input changes, that's the gain. I could also plot the angle, that's the phase shift, if you care. Normally you don't care, sometimes you do. Typically just care about the gain. So that's analysis. Given a filter, problem 3 looks at another type of analysis. Here's another filter. Plot its gain versus frequency. Again, that's pretty straightforward. Just pick your frequencies. S is j omega. The gain is just the way you write it. Plot the frequency versus magnitude, and I get this. This is a low-pass filter. Passes frequencies out to about 7 radians per second, then the gain drops off. That'd be like a subwoofer. Pass the low frequencies to your subwoofer, block the high frequencies. So that's analysis. Design is a little bit harder. With analysis, you're given the filter, find the gain versus frequency. In design, I want to go the other way around. Given the gain versus frequency, what's the filter? So what I can do is I can guess again, play around with this. You'll do that when you get to circuits, electronics, signals and systems. Right now, you don't really have a lot of background on filter design. This is where Matlab really shines. If you know nothing about filter design, you can design a pretty good filter using Matlab. And the trick is to use a function called fminsearch. So what I'm going to do is first come up with a function where I guess A, B, C, D, E, F, G. It returns the gain versus frequency, like we just did, and then calculates the sum squared difference. So here's the difference between the two filters. Return the sum squared difference in the two, then optimize it. Find A, B, C, D, E, F, G to minimize the difference. So the first step is to come up with a filter, or a M file, where I pass A, B, C, D, E, F, G. It calculates the gain versus frequency, compares it to what it should be, takes the difference, returns the sum squared difference. That's what this program does. For fminsearch, I want to just pass a single variable, that's a matrix. Parsing it, what Z means is that's my 6 parameters. For the gain versus frequency, I'm going to go between 0 and 10 radians per second, S is j omega, and here's what A, B, C, D, E, F, G mean. For what the filter should be, I'm going to do it in pieces. For frequencies out to 2 radians per second, the gain should be 1. Between 2 and 4, it's this equation, minus 2.2 omega plus 1.4. That's the equation for this line. Between 4 and 6, it's a straight line, 0.6. Between 6 and 8, it's another straight line. And otherwise it's 0. So checking that, I can go into Matlab. Where's Matlab? So I created that function called costf. I'm going to pass 7 parameters. It's going to calculate the gain, return the sum squared difference. Now let's try that. So costf, and let's try filter 1, 2, 3, 4, 5, 6, 7. How good is that filter? Well, what it did is it plotted the blue line. That's just to check to see did I do this part correct. And I kind of did that as a piecewise linear model. This is for frequencies between 0 and 2, 2 to 4, 4 to 6, 6 to 8. I added this guy in there just so I don't have to worry about greater than or equal. It's never going to be equal just because I offset everything by 10 to the minus 6. Just kind of a trick. Blue line is G ideal. The red line is my actual filter, and the sum squared difference is 424. Can I do better? So I can sit there and play around with the gains. So that's maybe a little bit better. I can kind of look at the way it's set up. B and C is the second order polynomial. So this is kind of in groups of 2. If I say let's try s squared plus s plus 4, that puts the poles at J2. 2 squared is 4. S squared plus s plus 9, that puts the poles at J3. S squared plus s plus 16, poles at 4. So here's the poles at 2, 3, and 4. Let's try 2, 4, and 6. It helps with Epin search to come up with a good guess. So here's pole at 3 and 36. Play with the amplitude. So again, I can kind of guess again, guess again. That's one way to design a filter. Or you can let fmin search guess for you. So there's a function in Matlab called fmin search. I want to minimize this function. And here's my initial guess. Now fmin search is going to play around with these numbers, basically play with the poles, move them around. And it does it a whole lot faster than I can. It also does a lot better job than I can. What you're seeing, I've got these 3 resonances. Those are your 3 complex poles. The complex part is the resonance. The real part is kind of the bandwidth. It's moving the poles around, trying to adjust them, trying to give me the blue curve. And it's kind of fun to watch. What this is doing, this is designing a filter. And it might have settled out. What I can do is take the previous guess, Z, try again. When it kicks out, it either kicked out due to max iterations or because that's the best you can do. So telling it to pick up where you left off, keep going. I've got a sum squared difference of 0.92. Looks like that's about the best you can do. Knowing nothing about filter design, I can design a pretty darn good filter using fmin search. That's part of the power of Matlab. If you know nothing about filter design, I can solve using numerical methods. That way when you get to signals and systems and you start designing filters for yourself, I can let Matlab design a filter and see if I could do better or get an answer similar to Matlab. What I can also do is use Matlab solution as my initial guess. And it turns out where I put the poles, here's one set of poles. One set of poles is at -2 plus minus j 4.7, so there's a resonance. There's another set of poles at 4 and 5, minus 1.6 plus minus j 1.74, and a third set of poles at minus 0.7 plus minus j 6.3. That's that resonance. And here's the resonance at 1.7. So there actually is a rhyme or reason to where you place the poles. You'll see that more when you get to 343 signals and systems. But for now, using Matlab, I can solve this problem using numerical methods. And that's the point of 111. Matlab is a really powerful program. Once you get used to it, I can solve a lot of problems, even if I know nothing about how to solve that problem other than using numerical methods. So when you're done, there's the answer I got, and there's my filter. So that is homework set number 14 for ECE 111.